Good morning, our students, and welcome to this morning's class. Today, we are still looking at some aspect of a binomial distribution. This morning, we are looking at the moment generating function. We already had a class on a binomial distribution discussing the probability mass function of a binomial distribution, and in the same class, looked at the expected value of a binomial distribution. In the second class we had on binomial distribution, we were so detailed proving the variance of a binomial distribution in a way and manner that the students will understand everything about the intricacies. So today we want to look at the moment generating function of a binomial distribution. So we are having binomial distribution, but we are talking about a moment generating function. Moment generating function. Moment generating function. This moment generating function is always written as a MGF. It's always written as what? MGF, moment generating function. So we are first of all going to begin with the formula for the moment generating function of any random variable x. The moment generating function of any random variable x is given as, we have m of x of what? Of t is given as e of tx. This is the moment generating function of any random variable x. That is how to write it. And of course, it is expressed as, this is we have that this is sum over the range of x of e of t of x of p of capital X equals small x. So it becomes the moment generating function of any random variable x that is a discrete random variable, or that is discrete in nature. Okay? Discrete because I am bringing in p of capital X equals small x, which of course is referred to as the probability mass function. Okay? So, and when we talk about probability mass function, we are talking about discrete distributions. So, it is the moment generating function of any random variable x, where this x is discrete in nature. So, it is we that is going to make it now to be moment generating function of either Bernoulli distribution, of either binomial distribution, of either Poisson distribution, of either geometric down the line. So, I will now say but. For binomial distribution, we know that P of capital X being small x is given as n combination x. P of what? X. Q of n minus what? X. Such that x takes a value 0, 1 down to n. So I will now say, therefore, the moment generating function of this binomial random variable x, which now is going to follow binomial, becomes m of x of what? T. Is now giving it the same thing as this, the same thing as this. So I will now say sum over the range of x. And of course, the range of x now is beginning from 0 to what? To n. So x is beginning from 0 to what? To n. Okay? So what we now have here becomes what? I have what? I have e of t of x. Then I have what? N combination what? X. P of x. Q of n minus what? X. I have something like this. Okay? So this time around, we are talking about the moment generating function of a random variable x that follows a binomial distribution. From moment generating function of any random variable x that is discrete, okay, to moment generating function of a random variable x now that follows a binomial distribution. So what do we do now here? What we do now here becomes that this is the same thing as we have sum that x is running from 0 to n. This thing contains x and this one contains x. So because both of them contains x, I can write this into be n combination what? X. Then I have this thing to be p of e of t, all raised to power what? X. Of q of n minus x. You can check what I have here. If you open this thing now here, you have this thing becomes e raised to power x. This thing becomes e raised to power tx, which is what I have here. Having arrived at this juncture, we recall for ourselves something. What we are going to recall for ourselves is this: that we are told that each time we have some from binomial expansion, each time we have sum of a combination r, a raised to power what? R, b raised to power what? We have n combination r, a raised to power r, b raised to power n minus what? R. Okay? Over the range that this is given as a plus b all raised to power n from binomial expansion. From binomial expansion. This over the range is given as this. So I would want to look at this and express this thing in that format. My sum is here, my sum is here. N combination R, N combination X. A raised to power R, PET raised to power X. B raised to power N minus R, Q raised to power N minus X. So I'm going to mimic this thing that is here. Here is my A. And look at where my A is. But in place of that A, what I have is PET. So I will now say PET. The sign I have here is plus. I have what? Plus here. What I have is what is B here. Look at the position of B here. Come in. The position of B is my Q. So I have that this is my Q. Then I will do this. Here is my N and it's raised to power there. And look at this my N here. So this. So this is the MGF of a binomial distribution. The moment you arrive at this now, you recall for yourself this binomial expansion. And from the binomial expansion now, you'll be able now to conclusively arrive at this. Permit me to bring my curtain down because the reflection of light is coming into the class. I think it's better this way. So this thing becomes the binomial distribution. Sorry, the MGF of the binomial distribution. So the interest is, having arrived at the MGF of the binomial distribution, like we earlier had said, from the MGF, in fact, that's why the name is called MGF, moment generating function. You can, from this MGF now, arrive at the expected value, arrive at the variance and the rest of them. Of course, you know that the expected value is the first moment about what? Zero. So the same thing is, okay, we now talk about now generating the moment from the MGF. You have already known that this is the MGF. So let us now see whether we can, from this MGF now, get the expected value and get the variance. So permit me to clean this. If you want to obtain the first moment about zero from the moment generating function, you are going to differentiate the moment generating function once and evaluate it when t is equal to what? Zero. What have I just said? That if I want e of x, first of all, the formula is always given as what? E of x raised to power r is given as what? D differentiating to the order of r of dt raised to power r of m of x of what? Of t. Evaluated when t is equal to what? Zero. So it is when this thing becomes one that they are talking about the first moment about zero. The first moment about what? Zero. And when this n becomes what? 2, you are talking about what? The second moment about 0. Okay? But remember that when we talk about what variance, oftentimes, what we're talking about is what is the second moment about the mean. So what we are going to do here, for us to find the expected value now, we are going to have what E of X. Here is going to be 1. And 1 is just like leaving it that way. So I will now come here. I'll say this is equals to differentiating this d with respect to what? To t. My moment generating function has been proven to be this. So I have what we call, I open a bracket here, I have what we call q plus p of e t, all raised to power what? N, evaluated when t is equals to what? 0. Okay. Are we there? Now, for us to differentiate this, it is better we make some definitions. Okay? Because I want to differentiate this, it is better we make some definition. I can say let eh, let z equals, I have q plus p of e raised to power t. And if z is equals to this, I will now say, therefore, I am now calling the whole of this one y. Okay, let me do it this way so you understand it better. I say let y equals, I have what? Q plus p of e of t all raised to power what? N. That's what I am saying here. Then I will now say, and I have that z is equals q plus p of e t. If y is this and what is inside this, is a therefore my y is equals z raised to power n. That's what it is going to be. So, and if I want to differentiate this y now, so I will now be able to say, therefore, my dy dt is now going to be given as what? Dy dz multiplied by, I have what we call dz dt. That is, I am going to differentiate y with respect to what? To z. I am equally going to differentiate what? Z with respect to t. And let us come by this side and say dy dz. Here is my dy dz. So here z is raised to power n. So I'll bring this n here. So this becomes what? N z raised to power n minus 1. That is how to differentiate that. You use the power to multiply the quantity and you subtract 1 there. So that one is done. So I want to differentiate this dz dt. So I have what? Dz dt equals. Where is my z? Look at my z here. I am differentiating this z with respect to t. This quantity q doesn't contain t. So it automatically becomes what? 0. Okay? So if I come here now, of course, derivative of e raised to power t is e raised to power t. So this is just the same thing like writing p of e raised to power what? T. So I will now come here and say, therefore, my e of x, which is what I'm looking for, which is now the same thing as dy dt, is the same thing as my dy dz is already my n of z of n minus 1 multiplied by, here is my p of e of t. And you and I know that I will now say, therefore, this becomes what? N. Look at n here. In place of this my z, I am going to write this. So I open a bracket this way. In place of this my z, I am going to write what? q plus p of e what t. I will cover it. Here is raised to power n minus 1. So here is what raised to power n minus 1 multiplied by what I have here is what p of et. So I have p of et. This is the derivative, the first derivative of this MGF about what is 0. And we are told to evaluate this thing when t is equals to 0. So I'm going to do this now when t is equals to what is 0. Anywhere I see t, I'm going to put 0. So this thing becomes what? N into. Here is my q, so I have my what? My q. Then I have plus. Here is my p, so I have my p of e. Here is my t, which becomes what? 0. Then I'll cover it. This is n minus 1. So here becomes multiplied by p of e. Here is my 0. So here becomes what? 0. This is the same thing as n into. Here is my q plus. Anything raised to power 0 is 1. Multiplied by this p will give me this p. Then raised to power n minus 1. Multiplied by anything raised to power 1 is raised to power 0 is 1. Multiplied by this p will give me this p. Remember that I earlier mentioned that p plus q is equals to 1. What I have inside this bracket is p plus q, which means what is inside this bracket is what? Is 1. So if I put in 1 here now, 1 raised to power anything is just 1. 1 raised to power 1 million is 1. 1 raised to power any damn thing is what? Is 1. So which means what I have here becomes that this is equals to what? N multiplied by 1 multiplied by p, which gives me what? Np. Don't you see that the answer is np? So the first derivative of the moment generating function of a binomial distribution returns what? Np, the MGF. Once you differentiate the MGF, the first derivative of the MGF, given that t is equals to what? 0, will give you Np. Okay? So that's aside. Now, for us now to obtain the variance now, we are going to talk about now the second derivative of this moment generating function. The second derivative of the moment generating function. So please, you permit me to clean here. Remember, I'm not going to clean here. This is where the first derivative ended. So permit me to clean this particular place. Oh, let me not even clean this one. Let me just put e of x raised to power r and cover it. So let me clean from here. Let me clean from there. Okay, what we have now is we are now looking at our e. We are now looking at our what? Our e of x raised to power 2. That is the second derivative. So here becomes what? D of raised to power 2 of dt raised to power 2 of m of x of what? Of t, evaluated when t is equals to what? 0. But good enough, we have had the first derivative and we arrived at this. So by implication, what this thing is this thing is equivalent to d of x raised to power 2 dt raised to power 2. This MGF is q plus p of et all raised to power what? N, evaluated when t is equals to what? 0. But we have had the first derivative and this is what we get. So this and this expression here is equivalent to having something like this. D of what? Dt. Instead of writing this, I am now going to write this, which is what we call n of q plus p of et all raised to power n minus 1 multiplied by or p of et evaluated when t is equal to what? 0. Because I've had the first derivative, this one. It's just for me to differentiate this one again now, then I will now be talking about the second derivative. And if you look at this thing, what we have here, we can actually use what we call the product rule, yes, of differentiation, where you tag the whole of this one here, from here to here to be u, and you tag from here to here to be what? To be v. And if you tag it that way, you'll be able to say that for you to differentiate it now, calling the whole of this expression either y, calling the entire expression either y, you can have that dy dt is going to be given as what? U dv dt. Okay? Plus. You have what? V du dt. And in that case, what you are going to do, here is u dv. So, and u dv is just like you writing, this is the u, you write the whole of this one, you write the whole of this. So, this is u, you write the whole of this thing. So, this thing becomes what we call n into q plus p of e of t of n minus 1. So, you differentiate what? V. And this is what you are taking v. Differential value of that v is just the same thing like p of e t. You have plus. So you permit me to clean here. Now, okay, so here you have v. So if you have v, you are going to write this. So you now write this the way it is. So which is p of et, p of et for this v. Du, you are now differentiating this quantity with respect to what? To t. And if you are differentiating with respect to t, this one will come down. So what you are now going to have is multiply by. This one coming down will give you what is called n into n minus 1. Because this n minus 1 will come, then you open a bracket, you have what you call q plus what? P of et all raised to power what? N minus what? 2. So you differentiate that what? U. The first one was v, which is just write this. Differentiate with v. Differentiating this v is just like putting the v the way it is, plus. Here is v, det multiplied by. Differentiating this thing with respect to what? To t. Then you now have, so dot, p of et. Differentiating this u with respect to what? To t. Here is my n, here is my n. Bring this n down, n into n minus what? 1. Multiply by that quantity minus 2 this time around, p of et. So you are meant now to evaluate this thing now when t is equal to what? 0. That's the implication. And evaluating this thing when t is equal to 0, here is t is equal to what? 0. So in that case, what you are going to do here becomes what we did before. Here this equals, here is my what? My n. Here is what? My q plus p of e raised to power 0. Then all raised to power n minus 1 multiplied by p of e of 0 plus. You come here, this thing becomes what? P of e of what? 0. Here is my n into my n minus 1. Here is my q plus what? P of e of 0. Close it. Of n minus what? 2 of p of e raised to power 0. In that case, what is actually going to happen here becomes what happened before. This is p, q plus p, which is equals to 1. 1 raised to power anything is that thing. So you have n multiplied by 1. Here is my p, you have my p here, plus. Here is my p, you have my p. Here is my what? Multiplied by n into n minus 1. Multiplied by anything raised to power what? This is q plus p. Raised to power, and q plus p is 1. Raised to power anything is that thing. So, and here you have your what? Your p. So here you have your what? Your p. Okay? So I will now quickly clean here. Permit me to clean this side. Permit me to clean this side. Okay, before I clean this side, let me use this space. Here will now give me NP. Here will now give me NP plus. This is my N into N minus 1. P times P will give me P raised to power what 2. And you know that we say that variance, the var of x, is given as what? E of x raised to power 2 minus E of x all raised to power what 2. And we have seen that E of x raised to power 2 has given us the whole of all this. So we now say this is equal. We have N P plus. Opening this bracket will give me what? What is the N squared P squared minus NP squared. That is, using this to multiply this will give it N squared. This one coming inside to meet it P squared. This will give me minus N. This one will now meet it minus. We earlier has shown that the E of x is what? NP. So we now have what we call NP all raised to power 2, which is just N squared P squared. By that, we are now seeing N squared P squared minus this, so that this and this can cancel. So we are left with this and this. And because we are left with this and this, we try to factor. I have NP here, open the bracket. Here it becomes 1 minus. What will be left here becomes what? P. And we earlier had said that 1 minus P is Q, so that this becomes NPQ, which is of course the variance of a binomial distribution. Thank you very much. Let us not expand the class quite much to manage the size of the video. This is how to arrive at the moment of a binomial distribution from the moment generating function of that distribution. Thank you very much.